Namaskar. Today's topic is Schwarz inequality and its applications. And as per syllabus, this is for the students of M.Sc Maths 4th semester. The paper is Functional Analysis 4C 6th. In this lecture, we state and prove Schwarz inequality in the first theorem. Also study some theorems as applications of this inequality. So this Schwarz inequality is also known as Cauchy-Schwarz inequality. Its statement is like this, that if x and y are any two vectors in a Hilbert space H, then modulus of the inner product of the xy is less and equal to norm x into norm y. So this is the statement of Schwarz inequality, that modulus of the inner product of xy is less and equal to norm x norm y. So we prove this easily. First, if y equal to 0, then norm y equal to 0 by the property of the norm, and modulus of the inner product xy equal to modulus of the x0 inner product equal to 0. Therefore, the result is true for this. That is, when y equal to 0, then both of this side of this inequality are 0. So now we let y is non-zero. So therefore, norm y is also a non-zero element. And then for any scalar, by the property of the inner product, we are having x plus by comma x plus by is greater and equal to 0, where b is some scalar we will choose later on. So then this implies we open this by the linearity of the h property h3, that x plus by plus by x plus by, that is greater and equal to 0, and then xx plus b bar. Here b bar we take from the second term outside this b bar, therefore here bar. B bar xy plus byx plus bb bar yy greater is greater and equal to 0. Now apply the definition of norm. This we can write as the norm of the x square plus b bar xy plus b xy bar. We write use the property h2 here, that yx is equal to conjugate of the xy bar plus modulus of the b square norm y square is greater and equal to 0, and this we denote as the equation number 1. So here we choose this b as particular case so that we will get a required result, and for this we choose this, that take b equal to minus xy upon norm y square in 1 we get, because we have taken y non-zero, therefore this denominator is non-zero, so we consider this, that the value of b is minus xy upon norm of the y square. We put this value in the equation 1, then we will obtain that norm of the x square minus xy bar xy upon norm y square minus inner product xy bar upon norm y square plus xy whole square norm y square upon norm of the y4, that is greater and equal to 0. So after simplification, this we will obtain that norm of the x square minus xy square modulus of the inner product xy square upon norm y square is greater and equal to 0, and this will imply that modulus of the inner product xy is less and equal to norm x into norm y. So we proved the Schwarz inequality. Next we consider the property of this inner product, that in a inner product space the inner product is jointly continuous, that is when if xn tends to x, yn tends to y, then both these two combinedly implies xn comma yn tends to xy. It xn tending to x and yn tending to y, then we will obtain that xn comma yn jointly continues to tends to xy. So the proof is that modulus of the xn yn minus xy equal to modulus of the xn yn minus xny plus xny minus xy. Here we add and subtract this x and y for the calculation point. Then we obtain applying the linearity that xn yn minus y plus xn minus x y. Then by the property of the modulus we can open this, and this is less and equal to modulus xn yn minus y plus xn modulus xn minus x y. And then by the Cauchy-Schwarz inequality we can write this as less and equal to norm xn into norm of the yn minus y plus norm of the xn minus x into norm y. Then we will obtain this tends to 0 because is xn tending to x, therefore norm xn minus x tends to 0. This norm xn minus x tends to 0, and similarly yn tends to y, then this norm yn minus y tends to 0. So this whole quantity tends to 0. So hence we can say that xn yn tending to x comma y, that whenever xn tends to x and yn tends to y, then xn yn jointly continues or tends to xy. Now the theorem third tells us that so that inner modulus of the inner product of the norm x into norm y if and only if x and y are linearly dependent. So here the Cauchy-Schwarz inequality with equal sign, that if this is equal then x and y are linearly dependent. So first implies part that let inner modulus of the inner product xy equal to norm x norm y. We denote this by the equation 1. Then to prove that, then we have to prove that x and y are linearly dependent, that is one is a scalar multiple of the other. So first choice that if y equal to 0, then inner product xy modulus equal to norm x norm y, and the set x y equal to x0 is clearly linearly dependent. Therefore, as the set of vectors containing 0 vector is always linearly dependent. A set which contains a 0 vector, then this set is linearly dependent. So no second case choice, that if y is not equal to 0, then norm of the y is greater than 0, and hence from the equation 1 we have modulus of the inner product xy upon norm y equal to norm x, or we take this norm inside to this, then we can write this as modulus of the x y upon norm y equal to norm x, and we assume z equal to y upon norm y, then we can write this as inner product modulus x z equal to norm x, where this z is y upon norm y, and therefore norm of the z equal to 1, and we denote this as the equation number. So this equation modulus of the inner product x z equal to norm x, where z equal to y upon norm y and norm z equal to 1, we denote this equation by, now consider norm x minus xz z square, then by the definition of norm, this is equal to x minus kz, where k is xz inner product. Then applying the linearity, we open this as xx inner product minus k zx minus k bar xz plus k bar zz. Then equal to, by the definition of norm, that this is equal to norm x square minus k bar plus k minus k bar plus k bar, because norm z square equal to zz equal to 1. So this is equal to norm x square minus modulus k square, and that is norm x square minus xz square inner product. Then by using 2, this is equal to 2. This is equal to 0. Therefore, we obtain x minus xz equal to 0, and this implies x equal to xz into z. Or rewrite the value of this z as y upon norm y, then we are having inner product x y upon norm y into y upon norm y, because z equal to y upon norm y. Then take this norm 1 by norm y outside, we obtain this as x equal to 1 by norm y inner product xy into y upon norm y, or xy upon norm y square into y. So we obtained here that x equal to ay, where a, the value of a is xy upon norm of the y square. So in this way we obtained x equal to ay, that is x is a scalar multiple of the y. So if the equality will hold, then we obtain that one vector is a multiple of the other, and therefore this is linearly dependent. So next, for the converse part, let x and y be linearly dependent so that one of them can be expressed as a scalar multiple of the other. So therefore we choose here, take here x equal to ay, where a is the element of the field. Then inner product modulus of the xy equal to ayy equal to modulus a into norm y square. So if we take here square and then under root, then we omit this here. We have omitted this square. So then this is by the, and the second part we calculate norm x into norm y equal to norm of the ay into norm y equal to modulus of the a into norm of the y square. So from these two we obtain that inner product modulus of the xy equal to norm x into norm. So thus when x and y are linearly dependent, then we can show that Cauchy inequality reduces to an inequality. Sorry, equality. Inequality reduces to an equality. The last we consider theorem 4, which tells us that norm of the x plus norm of the y equal to norm x plus norm y. Then prove that the vectors x and y are linearly dependent. So we prove this theorem with the help of previous theorem third. So we have given that norm of the x plus y equal to norm of the x plus norm of the y. Squaring both the sides, we get norm x plus y square equal to bracket norm x plus norm y square. So applying the definition of norm, we can write this as x inner product x plus y, and apply this here square, we obtain this as norm x square plus norm y square plus 2 norm x into norm y. Then we open this by the linearity or H3 property. We may obtain this equal to norm x square plus norm y square plus xy inner product plus yx inner product equal to norm x square plus norm y square plus twice norm x norm y. So we obtain here some terms cancels and the remaining terms are this sum of this is equal to twice real part of the xy, and in right side we obtain twice norm x norm y. Therefore, norm x norm y equal to real part of the inner product xy, which is always less and equal to modulus of the inner product of the xy, because the real part of the z is always less and equal to modulus of the z, and this we denote as the equation number 1. Also by Cauchy-Schwarz inequality we have norm x norm y is greater and equal to modulus of the inner product xy, and this we denote as equation number 2. Then from equation 1 and 2 we obtain that norm x norm y equal to modulus of the inner product of the xy. This shows that the Cauchy-Schwarz inequality reduces to an equality, and hence using the previous theorem third, we can say that x and y are linearly dependent. So in today's lecture we have considered the Cauchy-Schwarz inequality and discussed some other theorems as applications of the Cauchy-Schwarz inequality. For more detail, students can study the reference book on functional analysis. Thank you. I am Dr. Rpsomani, Associate Professor in Mathematics. Thank you.